Hello and welcome to this video on the graphing of a function. Alright, so if you recall, a function is a relation or a correspondence between two sets, and in this video it's going to be between two sets of real numbers, where every element in one set, called the domain, which will be represented on a horizontal axis, called the x-axis, every element of the domain will correspond to exactly one value of the range, which will be in the set known as the range here. The outputs will be represented by values on a vertical number line, known as the y-axis. So every element of the domain corresponds to exactly one element of the range, the definition of a function. And the way these are going to be graphed is very similar to a previous video I've done where I graphed an equation or graphed equations by the point plotting method. I'm going to make a table and plot, look at what ordered pairs belong to the relationship, satisfy that equation, and then plot those points, and hopefully we see enough to where we can form a pattern and then fill in the rest of the function, fill in the rest of the graph, the rest of that pattern. Alright, so let's see, I've just got a few examples for you today. So I'm going to be asked in each of these to graph each function, so I'm going to have three of them for you. Got f of x, function f, right, the value of function f at x, input x, equals negative 2 times x plus 9. So over here, the negative 2x plus 9 is an expression describing how the input x corresponds to the output f of x, right? Or in other words, how the input x corresponds to the output y. And the way I'm going to graph this is exactly the same way as I would have graphed the following. Alright, this is exactly like y equals negative 2x plus 9, right? Where my input's x, outputs y, right? Up here inputs x, and the output is f of x, the value of f at x. And very often, actually, you'll see in exercises where they ask you to graph a function, they'll say graph, y equals the function f at x, or y equals the function g at x, or whatever the name of the function is at whatever variable is the independent variable. And so you see how this is exactly like this, right? This negative 2x plus 9, right, is my function f at x. Right, that's interchangeable. So what I'm graphing here is exactly like this. Y equals f of x, y equals negative 2x plus 9, f of x equals negative 2x plus 9. Alright. So what I'm going to do is I'm going to make a little table where you see that y is alone, right? Y is solved for, or f of x is alone. So it would be easy to find outputs. It would be easier to find ordered pairs on this graph, points on this graph, if I plug in a value for x. Right? So I'm going to make a little table here where down one column, again if you want to make rows that's fine, but down one column, plug in different values for my input, different arguments, right, for the x there. Down the second column, the outputs, right, the values of f at these x's. And I'll just write the equation again to describe, show how those outputs are going to be calculated. And then in the third column, basically the points we're going to plot, the ordered pairs that belong to this function. So in ordered pair form here, the x coordinate, comma, at the input, and then the y coordinate, or the f of x, the value of f at x, that's the y coordinate, right? Whatever the value of f at x is, that's the output. All right, we'll plot this ordered pair. All right, and as with, again, if you've seen my videos on graphing with point plotting, we're just going to plug in a bunch of inputs. Right? I'll do at least 5, and hopefully we'll see enough points, plot enough points to figure out what the rest of the graph's going to look like, right? Enough to where we see a pattern and can make a very educated guess as to what the rest of the ordered pairs in the function look like. Alright, so what I like to do is I like to plug in my values so that they're centered around 0. Alright, you don't have to do these 5, but I like to start off with these 5 in most cases. So I'm going to plug in -2 for x, -1, 0, 1, and 2. Now I wouldn't use these if they weren't part of the domain, right? If any of these values made me divide by 0, right, or take even roots of negative numbers or logarithms of non-positive numbers, things that wouldn't result in a real output, then I wouldn't use them. But here I'm not seeing any denominators with variables, right? So I can see that the domain of this function is all real numbers. I can plug in anything I want for x. Okay. Alright, so then how the output is calculated. Well, the value of f, this function, the output, at -2, right, just replacing x with -2, is, now I'm just going to write it, it's -2 times I'll write it out this time, -2 times -2 plus 9, that's +4 plus 9 is 13, right? So the point I am going to plot, right, the ordered pair I'm going to find the location of on the xy plane. Input -2, x coordinate -2, and then the output is the value of f at -2, which we see as 13. Right, so I'm going to plot that ordered pair in a little bit. Then -1, right, the value of f at -1 is, and just to avoid some clutter here, I'll just say this out loud. It would be -2 times -1, which would be +2, plus 9 would be 11. Alright, so input -1, the output is the value of f at -1, or f of -1, which we see as 11. Plot that point. The value of f at 0 is -2 times 0, which is 0, plus 9 is 9. So input 0, output f at 0. So 0, 9 I'm going to plot. Input 1, the value of f at 1. The output at 1 is -2 times 1 is -2, plus 9 it would be 7. So input 1, output 7. And finally here in this table, f at 2. The value of f at 2 is -2 times 2, which is -4, plus 9 be 5. Right? So input 2, output 5. Great. Alright, and that's just 5 of them, right? And I could do that forever. I don't have to plug in these 5. I could plug in, -1.5, -3/4, 5,000, 1/7, pi, square root of 3. It doesn't matter. And I'd get some ordered pair. I'd get some output. And there should only be one output. Remember, these are functions, so no matter what I plug in, I should only get one real number output. And now that I have these, let's make a graph. Right, let's see what this looks like. All right, so here's my graph paper, and you don't have to do it on graph paper if you want to, try to do it by hand. Just try your best to make straight lines and stuff, and nice evenly spaced notches on your axes, and be consistent with the spacing. All right, so the first point in one of the points that belongs to this function, called f, be -2 for the input, 13 for the output. Now I'm going to have each square here represent 1 unit on the x-axis, and also for the y-axis I'm going to have each square represent just 1 unit. So -2 on the x-axis, and here's the origin, 0, 0. I'm going to go 2 to the left, right? -2 on the x-axis, and then 13 units on the y-axis, right? Positive 13. So that point is this point up here, right? That's in line with -2 on the x and 13 on the y. This location right here. Okay, there's an ordered pair. There's a point in this function. And then -111. -1 input, -1 on the x-axis, 11 on the output on the y-axis, and that's this location here. And 0, 9, pardon me, 0 on the x, so we're on the y-axis, and then I go to 9 on the y-axis. That's this location here. Alright, and that would be called the Y-intercept. Right, it's a point on the y-axis, has an x-coordinate of 0. 1, 7, right, so positive 1 on the x, 1 unit right, 7 units up, right, that's this location here. It's in line with both of those. And hopefully even after just these few, you can see that all these ordered pairs that belong to this function, all these relationships between inputs and outputs look like they fall in a nice straight line. And they do. Alright, one more of these. How about positive 2 for the x, and then 5 for the y, and that's this location here. Alright, so it definitely looks to me, even though it's only 5 solutions, I'm getting a straight line vibe here, right? It looks like all these fall in a straight line. So I'm gonna draw that in. Alright, because I mean there's infinitely many ordered pairs in this function, right? Infinitely many solutions to this equation. But you're not going to be able to list them all. Alright, so what we're doing is just putting enough out there to where I see a pattern and I can, kind of guess where the rest of the solutions will fall. Alright, so let's do that. Alright, so I'm going to use a nice ruler. They all fall in a nice straight line. And here we go. Alright, so looks like this here. Alright, and that pattern does seem to continue. It doesn't look like it would stop anywhere, so I'm going to put little arrows to indicate that the graph is going this way forever, and a little arrow down here to again indicate that the graph looks, the solutions will be going this way forever. Great, and there we go. That is the graph of this particular function called f. And in fact, you might see in some textbooks some pictures where they'll actually label this graph here represents function f. They'll put like the name of the function next to the graph, so you know what function they're talking about. Because if I had to graph multiple functions on the same axes, the same coordinate plane, I'd like to label so that I knew which graph was for what function. Alright, wonderful. But do you see how that was no different really than, again, a previous video of mine? If you haven't watched it, go ahead and check that out, or look for other people's videos on graphing using point plotting. It's the same procedure. I plug in a variable, I plug in a value for my independent variable, which is in the parentheses, right? The name of the function comes first, then you have your independent variable x, the input. I plug in a value for that, and then calculate the output, which is the f, right? The output is represented by the name of the function. That's my dependent variable. And plot enough to where you see a pattern and fill it in. Alright, so I just got a couple more. Let's take a look at this one. Alright, so here I'm graphing the value of f, another function called f. The value of f at input x equals, and then here's how you calculate the outputs, x squared plus 2. Alright, so same deal. I'm gonna make a little table for this, and remember f of x, this is the output. This represents basically the y, right? This is just like having y equals x squared plus 2, if you want to rewrite it that way. Alright, so I'm gonna make another little chart where my input is x, right? So down one column here, I'm gonna put values of x. And down the next column, the outputs, which are the values of the function f at x. Alright, and I'll put how we're going to calculate that. Just write the equation again. And then in the third column here, just to keep track of things, make it easy on myself, just the ordered pair, the point that I'm going to be plotting on the coordinate plane. So the ordered pair will have my choice of x as the input, first coordinate, and then the calculation, the value of f at x as the second coordinate. Pardon me. Alright, so same deal. The domain looks like it's all real numbers again. I can plug in whatever I want because there are no denominators with variables, there's no even roots, there's no logarithms. So I see that I can plug in whatever I want. So just like the last example, I'm going to plug in these 5, the same 5 numbers, -2 to 2. So -2, negative 1, 0, 1, and 2. And if you want to plug in more, fine. I might even do a few more. This is going to give me 5 outputs, 5 points to plot. I might even put in a couple more just to really hammer home the pattern at the end. Or if I don't see the pattern, do a few more until you do see it. Alright, so then when the input is negative 2, what's the value of f at negative 2? Alright, so that's negative 2 squared. Now be careful. Alright, I like to put parentheses around whenever I replace something. I'm replacing x with negative 2, right? So I'm going to put parentheses around that. Negative 2 squared plus 2, and then that's being squared, meaning multiplied by itself, right? Negative 2 times negative 2, that's positive 4. Too often people make the mistake of writing just minus 2 and then squaring just the 2, but you're squaring the negative 2. Alright, so it's not negative 4, it's positive 4. And then you have plus 2, which would make that 6, right? So the ordered pair I'm going to be plotting, the point I'll find the location of has negative 2 for the input, my value of x, and then the output, the y coordinate, is the value of f at negative 2. And the value of f at negative 2 we saw was 6, right? So the ordered pair, negative 2, 6. What's the value of f at negative 1? Alright, so again, I'm not going to write so much so it's all cluttered. We're squaring the negative 1, right? I mean, negative 1 times negative 1 squared is positive 1, plus 2 is positive 3. So I have input x, negative 1, output, the value of f at negative 1, positive 3. And then what's the value of f at 0? Well, that'd be 0 squared, or 0 times 0, which is 0, plus 2 is 2. So input 0, the output is the value of f at 0, which is 2, so I'm going to plot the point 0, comma 2. Then f of 1, the value of f at 1 is 1 squared plus 2, 1 plus 2 is 3. So I have input 1, output 3. And the value of f at positive 2 is 2 squared, which is 4, plus 2 is 6. So input 2, output 6. And again, this is just 5 ordered pairs that belong to this function. There are infinitely many. You can choose whatever you want for x. There are infinitely many values. So there's no way I'm going to list them all. What I'm going to do is plot these 5, see if I see a pattern. And if I see a nice pattern, I'll just make an educated guess as to where I think all the other ordered pairs are and fill in the graph. Alright, so here's my graph paper again. Again, you don't need graph paper. I just trying to make it look nice. That's all. Again, if you're using no graph paper, just try to make your axes as straight as you can, and make sure that the notches you mark off are consistently spaced. All right. So again, in this particular picture, I'm going to have each square represent 1 unit on the x-axis, and I'm going to have each square represent 1 unit on the y-axis, right? Alright, so plotting the point, negative 2, 6 in this function. So negative 2 on the x, the horizontal axis, and then positive 6 on the vertical axis. And that is, this location right here that's in line with both of them. So there's one point, there's one ordered pair, that negative 2, 6. And if you want to label it, fine. Negative 1, 3. All right, so I have negative 1 on the x, positive 3 on the y. That is this location here. All right, got 2 points, 2 ordered pairs in this function. 0, 2. So 0 on the x, which means I'm on the y-axis, and then 2 units on the y, 2 units up. That'd be this location here. This is again what they would call a Y-intercept. Alright, it's a point on the y-axis, has an x-coordinate of 0. Alright, then I have 1 for the x, 3 for the y, 3 for the output. This location here. Pardon me. And then finally, 2 for the x, 6 for the y. 2 for the x, 6 for the y. This location right up here. Alright, so definitely not like the last example, right? This is definitely not going to be a straight line, right? These points look like they're forming more of a weird U shape. And this actually has a name. When one of the variables is squared and the independent variable is squared and the dependent variable f is not squared, so the first power. When that happens, you get a graph called that has a shape called a parabola. So this is going to have actually a shape of a parabola. Now, if you want to plot some more points, I mean, 5 points is fine, but if you want to plug in, maybe 1.5, get a point here, -1.5, get a point here. I'll just plot a couple more. All right, I'll just say them. You don't need to write them. So when x is 3, 3 squared is 9 plus 2 is 11. So I get the output. The value of f at 3 is 11. So 7, 8, 9, 10, 11. Right. So input 3, then f at 3 is 11. There's another ordered pair in the function. And the same thing would go for -3, wouldn't it? Right? When x is -3, -3 squared is -3 times -3, that's +9. Then plus 2 is +11. So the value of f at -3 is 11. There's another location. And hopefully you can see that this would just keep getting larger and larger on both ends. Right? As I go to the left, it would go up. As I go to the right, it would get larger and larger, go higher and higher. If I plugged in 4, I'd go to 18. Same thing for -4. I plug in 5, I'd go to 27. And same thing for -5. So I'm getting this picture here. And not a straight line, more of this U shape. And one thing I do want to point out about parabolas, these U-shaped graphs, they're not pointy down here, they're more curvy at the bottom, right at the point called the vertex. So make it more curvy, not like a point, it's not a V shape. And then it continues on, and again, like I said, it looks like it's just going to keep getting higher and higher that way, so I'll put a little arrow here. And same thing in this direction, so a little arrow over there. Great. And there we go. There's a complete graph of this function called f. And again, you might see this in some text where they label next to the graph the name of the function that is the graph of. Little f there. And great. All right, it's the same point plotting procedure. I plug in a value for the input, then use the equation to find a value for the output, and then I'll have an ordered pair, an input and an output pair to plot on my coordinate plane. And once you've found enough to see a pattern forming, you can make an educated guess as to where all the other ordered pairs of the function fall, all right, where all of them lie, and fill it in. Wonderful. All right, so I've got just one more of these. A little different than other videos I've put up. Here we had a graph of a straight line. We had a graph of a parabola. And here I have what's called an absolute value function. All right, I'll write that out here. So I haven't had these really introduced in my videos yet. So this is f of x equals these large bars on the side of an expression are the absolute value symbols. All right, this is an absolute value function. Okay, these symbols, this means the absolute value of x. So this is the absolute value of x minus 2. And you can think of the absolute value as, it's a non-negative number, right? It's the non-negative distance that x is, or whatever the number is inside, is from 0. Okay. So some quick examples here. The absolute value of 3. 3 on the number line, if you think about it. Here's a number line. Here's 0. Right? 3 is 3 units from 0. So the absolute value of 3 is simply 3. The absolute value of -3, however, is not negative 3. All right, it's non-negative. All right, absolute value. Whenever you take the absolute value of a number, of an expression, the resulting output is never negative. So the absolute value of negative 3, well, let's look at where negative 3 is. That'd be over here on the number line, and again, that is 1, 2, 3 units from 0. So this is also 3, positive 3. All right, the absolute value of 2 would be 2. The absolute value of negative 2 would also be 2. Again, all positive numbers. The only one that doesn't have a positive output is 0. The absolute value of 0 is 0, right? It's no units away from itself, and that's the only one that doesn't end up being positive. But everything else, the absolute value of any other number is positive, right? And the absolute value of 0 is 0. Okay, so hopefully that made some sense, right? When it came into in regards to the number line. Now let's get back into my function here. Right? Let me make a table, just like the last two examples. So down one column, my inputs, right? The values of x I'm going to plug in. Then the outputs, the values of the function f at x, and how they're calculated in this second column. And the third column, the points I'm going to plot on the coordinate plane, where and here's how they look. The ordered pair, the first coordinate will be my choice of x, and the second coordinate will be the value of f at x. All right. Great. Alright, so and just like before, I'm not seeing any stuff in this expression that would give me a non-real output. There's no variables in denominators, no variables inside even roots or logarithms, so I'm not seeing any choices of x that would give me a non-real output. So I'm good on the variable x. I can plug in whatever I want, and just as with the last two examples, I personally like to start off with those 5 around 0 if they're allowed, right? And they are allowed here. So negative 2, negative 1, 0, 1, and 2. Again, you can start with whatever you want. It doesn't have to be these 5. I personally just like doing these 5 to start. And if I don't see a pattern after these 5, I will plot some more. And I might do that here. Alright, so the value of this function at negative 2 is the absolute value of negative 2, right, for x minus 2. Right. Now be careful. People tend to make everything positive in here. You got to simplify what's inside first. The absolute value symbols are like parentheses. They're like grouping symbols. You simplify what's inside first, and then take the absolute value. So this is the absolute value of, and then what is negative 2 minus 2? That's negative 4. And the absolute value of negative 4, I think where negative 4 is on the number line here, that's 4 units away from 0. That's positive 4. Alright, so I have input negative 2, output positive 4. The value of f at negative 2 is positive 4. I'm going to be plotting that point, negative 2 comma 4. Okay. Same thing for the next one. What's the value of f at negative 1? Sorry about the clutter here. Now remember, you would simplify what's inside first. What's negative 1 minus 2? That'd be negative 3. And then take the absolute value. So that's positive 3. All right. The absolute value of negative 3 is positive 3. So negative 1 for the input, and then the value of f at negative 1 is positive 3 for the output. I'll plot that point. And then what's the value of this function at 0? Again, you simplify what's inside first. 0 minus 2. 0 minus 2 is negative 2. And the absolute value of negative 2 is positive 2. So I'm plotting the point 0 input, positive 2 output. The value of f at 1. Again, simplify what's inside the absolute value symbol first. Replace x with 1, that's 1 minus 2 in there. 1 minus 2 is negative 1. Then the absolute value of negative 1 is positive 1. So ordered pair input 1, output 1. 1 corresponds to 1. and then the value of f at positive 2, and replace x with 2. 2 minus 2 is 0. Okay, 2 minus 2 is 0, and the absolute value of 0 is 0. Alright, so I'm plotting this point, input 2, output 0. Alright, so I'm going to start with these 5 and see what happens. Okay, now I'll warn you here. It's going to look like one thing is happening, but I will assure you that something else is. I'm going to actually be plotting more points here in a second. But let's see what it looks like right now with just these 5 points, these 5 ordered pairs that belong to the function f. Alright, so again, I've got my axes drawn up here on my graph paper, and let's plot some of these points. And just as before, I'm going to have each square on the x-axis, each notch represent 1 unit, and each square on the y-axis will also represent just 1 unit. Alright, so the first point, negative 2 on the x, positive 4 on the y, and that location is this point right here. So there's the first point, negative 2, 4. Then negative 1 on the x, 3 on the y, negative 1, 3 for the second location. Then 0, 2, 0 on the x, 2 on the y. Right, and so far it looks like the points are forming a nice straight line. Then we have 1, 1, 1 for the x, 1 for the y. This location. Alright, and then we have 2 for the x, 0 for the y, right? So this one would be on the x-axis. This would be called an x-intercept of the graph. Alright, now here's what it's a little deceiving, these 5 points, because you might think, oh look, I've drawn 5 points, they look like they're all forming a nice straight line. So if I draw this part of the line in, great. All right, in fact, I will do that. All right, I'll draw this part of the line in where all the y coordinates are positive or non-negative. Right, so just this part of the line here, and that's fine. Looks like it's doing that, doesn't it? All right, looks like it's doing that. And notice that every single one of these points I just drew has a positive y coordinate, right? This point has positive 2 as a y coordinate, this point has positive 3, this point has positive 4, positive 5, positive 6, and so every single one of these has a positive y coordinate, which it should, right? This function is the absolute value of a number. And so the absolute value, remember, is always going to be positive unless it's 0. So this is where it gets deceiving, right? It looks like from those 5 points that I've got, a straight line going that way. But what about the other way? If I continued this, all right, now I'm not going to draw it, but if I were to continue this and draw points, and it looks like this would be another point and this would be another point. What's wrong with this is that these points down here have negative y coordinates, negative outputs, but this is an absolute value function. The absolute value of a number is never going to be negative. So these points down here and here and here following that line, these points down here cannot be on this graph. So that tells me that I've got to keep going, right? That these 5 points, sure, it's good enough for this side because all these points on this side have positive y coordinates. You're going to get those. But it's not good enough for this side of x equals 2. So let's see what would happen. All right, so I'm going to continue the table. All right, it looks like we're being deceived here by my picture, but I have to know something about my function. Absolute values can never be negative, right? The absolute value of a number can never be negative. So now I'm going to continue on. Plug in 3. What would be the value of f at 3? So plug in 3 for x, 3, and then simplify what's inside first. So like I said, it's like parentheses, these absolute value symbols. You simplify what's inside first, and then take the absolute value. So 3 minus 2 is 1, and then the absolute value of 1 is 1. So I'd have the ordered pair with an input 3, output 1. Let's plot that. So input 3, output positive 1. Again, notice that it is positive, right? The absolute value of a number is never negative. And look at what happens. So this is not a continuing straight line down here. It looks like it makes a turn at this point 2, 0 to stay, so that everything, all the y coordinates stay positive. And can you see how I'd have 4, 2, right? If x were 4, I'll just say it up here. Put in 4 for x. 4 minus 2 is 2, and then you'd have the absolute value of 2, which is 2. So I'd have input 4, output 2. I'd have 5, 3, right? If I input 5 for x, 5 minus 2 is 3. The absolute value of 3 is 3. I'd have input 5, output 3. And can you see how I'm still getting a straight array here, technically. This is called a ray when you have a line that actually ends at one point. It's called a ray. So I have a ray here, and it looks like I have another ray of points over here. All right. So let me draw that in. It looks like that's going on, and it would continue to go on that way forever. So you see this weird looking absolute value function, all right? When I take the absolute value of some number, it's always going to have positive outputs. All right, so see how it never went below the x-axis, stayed above the x-axis, and it was on the x-axis here, but that's where like it turned. So I've got this like weird V shape, right? A very sharp V going on here with this absolute value function. So, yeah, so be careful. As I said, you can start with 5 points, but you also have to pay attention to what the function is. What does it mean? What does absolute value mean? You have to pay attention to the function, and you might be deceived by 5 points. You might have to plot more, like I did here. I plotted 8 points here, and finally figured out, this graph's got to stay above the x-axis, right? Because it's absolute value. Absolute value is always positive. All right. So just again, be careful. You might think you're seeing a good pattern sometimes, like I did with the first 5 points. I was like, oh, it looks like a straight line, right? But just pay attention to the function as well, what the function means, before you decide that I am completely satisfied with my pattern. All right, wonderful. So again, still the same point plotting method. Plug in values for your input, calculate values for your output, plot points, and plot enough points, whether it be 5, 8, 10, 12 points. It doesn't matter how long it takes, until you're satisfied with a pattern, and then fill in that pattern. Now obviously with more experience, you'll be able to look at a function and kind of know what the graph's going to look like based on the way the function looks. And if you and later too, when you go into, if you ever go into a calculus class, you're gonna not always start off by just plotting a bunch of points. You're gonna find special critical points, very special values that are associated with the graph that make plotting the graph a lot easier. But for right now, in this beginning intermediate algebra setting, your best bet is to just gain experience by practicing this point plotting method. And hopefully after enough examples, after enough exercises, you'll come across certain equations, say, it's the absolute value of some linear expression, some x to the first power expression. That graph's going to be a V shape, or aha, I have an expression where x is squared and the output f is to the first power. That's going to be a parabola shape. Or I have just x to the first and y to the first, x to the first power and f to the first. That's going to be a straight line. Hopefully with enough experience, you will just be able to look at an equation and know what kind of a graph you're going to get. All right, and then plot points from there. All right, so great. So as I like to say at the end of all these videos, try the best you can, do the best you can to try to understand and get the material beforehand on your own, before you go looking for help. I find that material tends to stick better with people when they've put in the time and the effort to really work on it on their own and get it on their own tends to stick with them longer, and they're more proud of it for something. Um, so read the material, of course. Read the author's examples, perhaps even try to work out solutions to some author's examples before you see how the author did it themselves. See if you can learn from any mistakes there. Practice problems, practice exercises, look up solutions when they're available to check yourself. And don't just give up after the first attempt or the first 2 attempts. Try it several times, several different approaches. And if after several attempts at a problem, it's still not working for you, it's still not clicking, maybe you should go back and read the material again, a little more carefully, a little more slowly. Perhaps even a third time. Because who knows, maybe that second read through, third read through, you'll see something that you didn't see the first time, or something will click in your mind that didn't make sense the first time, and they'll make the problems that much easier. But if after several read-throughs of the material, after several attempts at problems, you're still not getting it, it's still not clicking, then it's not a sign of weakness whatsoever to go out looking for help. That is what other people are there for. So ask a teacher, a tutor, a friend, someone in the class who you know that knows the material well and is willing to help. Look for supplemental materials online. There is lots of stuff out there. I'm sure you'll find whatever you're looking for. Look for videos on the subject, like this one, or plenty of other ones out there that are better than this one. I assure you they are out there and you can find them. But just keep at it. Stay persistent, keep practicing, and try to stay positive. That's the hardest part. Trying to keep a positive mindset, keep an open mind, think I'm going to enjoy learning this, I'm going to enjoy reading through this material and taking something away from it for my class and for my own mind, and just stop saying that you're going to hate math and that you've hated math your whole life and never been good at it, because it's amazing the difference that a positive attitude can make. So just stay persistent, keep practicing, stay positive, don't give up, and I know you're going to get it eventually. All right, so thank you for watching.